Okay, so any questions?
So 2 questions. The first question is, like, for the problems that we had for homework, would we have to write the transition states on the test or no?
No.
Okay.
Because the transition states, that's too many dotted lines with the resonance hybrid. So you did not have to write transition states for the homework, nor would you have to write transition states for the exam. Number 2.
Could you go over, like, either of them?
Sure. If I can get there. Let's take that one. So let's just add HCl to this to shorten the number of steps. I asked you to write H plus and then H2O. So you'd have to add the H plus, then add the water, then lose the H plus to get the final alcohol product. But so it's not exactly the same problem. Let's just do HCl. So where am I going to add my H plus in this molecule? To which carbon? One, 4. Are we all agreed it should go to 1 or 4? So we would add the H plus to carbon. In this case, since it's symmetric, it doesn't matter. So we would go ahead and add the H plus to carbon 1. Right, why am I not adding to carbon 2 and 3? Kevin?
If you do, then you won't have any, then it won't have different forms.
So, did anybody add to carbon 2 and 3? The H plus to carbon 2 and 3? And I kind of talked about that at the end of class on Wednesday. But, so if I add the H plus to carbon 2, yes, I'm going to make a tertiary carbocation, but I'm only going to make 1. It doesn't have a resonance structure. So if I now take my first carbocation and I draw my resonance structure for it, then I'm now still going to have a tertiary carbocation. So either way, if I add to carbon 1 or 2, I'm going to get a tertiary carbocation. The problem is, if I add to 2, that's all I get. Whereas if I add to carbon 1, I'm going to get my tertiary carbocation plus my other resonance structure. So again, what we're doing is we're taking the broadest interpretation here of Markovnikov's rule. We're saying we're going to write the most stable intermediate. And sometimes that isn't adding the H to the carbon with the most hydrogens. Okay, the broadest sense is the most stable carbocation, and that outrules the number of hydrogens like this case. So there's my 2 intermediates, which is what you would have started with. Now, you would have added H2O to each one of those carbocations, gotten an oxonium ion, lost H plus to give you the final product. So what I'm going to do is I'm just simply going to take my Cl minus, and I'm going to add my Cl minus to this carbocation and add my Cl minus to that carbocation. And again, what I really should be doing is I should be adding my Cl to the resonance hybrid. But that gets to be too complicated in terms of where does the double bond go. So it's easier just to treat these 2 resonance structures as if they were each intermediates. And so there's my 2 products. This one is my 1,2. This is my 1,2 product, and this one is my 1,4 product. Now, if you're having trouble with adding the H plus and writing the resonance hybrid from sort of this forward mechanism, you could always just, if you're able to write the 1,2 and the 1,4 products, you could start by writing those and then removing the Cl to form the carbocation, because that's where the carbocation is where the Cl is. So if you can write the 1,2 product and the 1,4 product, then what you can do is then you can just simply erase the chlorine and go back up and form the carbocations. If you're having trouble doing this sort of in the forward way, there's kind of a backdoor way of doing this. And then wherever you add your carbocations, that's where your Cl minus attacks. So what's left? So what do I have left? I got my resonance hybrid. So in order to write the resonance hybrid, I need to average the two structures of the allylic carbocations. So I'm going to write all my single bonds in place. And now I'm going to average, and I'm averaging these two. These are my two structures that I'm going to go ahead and average for my hybrid. So single bond, single bond, single bond, single bond, double bond, partial double bond, double bond, single bond, partial double bond. So average the bonds. Now average charges. Plus, 0, delta plus, 0, 0, 0, 0, plus 1, delta plus. So everywhere that there is a plus charge, there's going to be a delta plus in the resonance hybrid. Everywhere there was a double bond after the first addition, that's where there's going to be a partial double bond. And the partial double bonds will be sort of bounded by two delta plus charges, is the way that these systems work. Okay, but we always add the H plus to carbon 1. So the only difference in the problem I asked you to do was there's an extra step of adding the water to form the oxonium ion, then losing H plus. And again, you don't have to write the transition states for this, just the actual intermediates. Okay. What else? I think there's still a few of these in the February 20th folder. The February 20th folder under practice problems. And there's a narrated answer key that goes with them. And then there's other practice problems like this 1214 edition on the old exam 2s. There's probably plenty of those in old exams because I always ask. I always ask for this. What else?
Wait, just for Top Hat, when are you going to get rid of like the questions we don't need to do, just so we know that we didn't skip them?
I guess today. I was intending on doing that sometime before today, but I didn't make it. They all have to do with molecular orbital theory. So anything with those orbitals, you won't. But I'll send an email out on which ones not to do, because I don't want to delete them. I just want you not to do them. Okay, so. All right, so the way we progress through looking at the allylic carbocation or allylic systems, then moving that up to conjugated dienes. The reason that we take the material in that order is because now I'm going to go to the ultimate conjugated system, which is a benzene ring or an aromatic ring. So a benzene ring or an aromatic ring has alternating double and single bonds in a 6-membered ring. It's the ultimate conjugated system because it doesn't have a beginning and it doesn't have an end. It's cyclic. And so there's the two terms we're going to use is benzene ring. This is benzene C6H6. And also aromatic. Aromatic means two things. Number one, these compounds do have an odor, or I wouldn't call it a fragrance, but they certainly have an odor. So that makes them aromatic. Mothballs, if anybody still uses mothballs, I don't know, I haven't seen moths come out of my closet in a while. If they're in there, they're probably in there for good. But mothballs is like naphthalene, which I'll show you the structure of, or it can be 1,4-dichlorobenzene, but it has that smell that moths don't like. That's an example of it being aromatic. Like the tolididine that we used in lab this week had kind of a disagreeable smell. So that's one interpretation of aromatic, but it's not the one we want to use. Aromatic also means very stable, like super stable. And so we're going to kind of go through what makes a molecule aromatic, what are the rules, work our way through just normal molecules in terms of not being charged, and then we'll work to anions and atoms with nitrogen, oxygen, or sulfur in their rings, heterocyclic compounds. So a couple things structurally about benzene. Benzene is flat, as you can see in this picture. The benzene is flat. All the carbon-carbon bonds are the same length. They're all in between a single and a double bond. But this molecule is flat. And that is a characteristic of aromatic compounds. Molecules that are super stable and aromatic are flat or planar. There was a big controversy about what the structure of benzene was back in the early 1900s. What everybody knew was the benzene was C6H6. They knew what its molecular formula was, but they didn't know how to put the structure together. And there were a lot of different things that people proposed. The only one I can kind of remember is they thought it might look like that, where there were single bonds between the opposite carbons. So there's actually very old organic textbooks that have a whole chapter on these are the three proposals right now, and there's pretty good evidence that it's what's called the Kekulé structure. And now we know that is the case, and that's what's accepted. So we know that it's alternating single and double bonds, but the issue is how do we order the single and double bonds, because there's two different methods of doing that. Of course, now we know that they're resonance structures of each other, and the real resonance hybrid of those two would have dotted lines on all the bonds, and that makes a circle. So that's why you see benzene ring with the circle in it. I think I've broken myself of the habit of writing the circle in there because there are times when we really need to see the bonds. But they can be oriented either way, and actually neither of these two are correct, right? We know that it's a resonance hybrid. So these two structures are ultimately what we found out it was, and they're what they're called the Kekulé structures. And the reason they're called the Kekulé structures is because of Auguste Kekulé, who proposed that it was alternating single and double bonds. And the story of that is that, he's working on this problem, has a few adult beverages, falls asleep by the fireplace, and then has a dream of snakes, where the snake wraps around and grabs its tail. And so from that, he proposed that it was a cyclic ring and that they had alternating single and double bonds. It wasn't obvious at the time that these two structures were not independent structures and that the molecule didn't flip back and forth rapidly between them. They actually, what they had to look at was putting two groups, let's say, next to each other on the ring and saying, oh, these would be two different structures if there was a double bond between the methyl groups or whether there was a single bond between the methyl groups. And what they couldn't do is they couldn't find two compounds. And so that led to the idea that, well, maybe they're rapidly interconverting, but then ultimately led to resonance. And we know now that they're not rapidly interconverting, right? That's not what resonance structures do. And my example of that, because I'm obligated to give you the absurd example of what that would mean, would be if we took a pit bull and a chihuahua, or better yet, we could take a Doberman and a chihuahua, and we could have them have a baby puppy, and that would not be constantly switching between Doberman and chihuahua. As cool as that would be, right? And you know all of this from genetics, right? Because it's the same thing that happens there. Although there was a Super Bowl commercial where they put a Doberman's head on a chihuahua body and had it chase a car. And I thought I was going to have to sue them because they took my idea. I forget what it was called. It was like a Dober haha or something like that. It was the idea that, you can have hybrids. So it wasn't obvious back in the early 1900s, once this was all resolved, that resonance structures didn't constantly switch back and forth. But this is the work on benzene is what gave us our resonance theory that we have today. So that was what Kekulé did. And so then we have partial bonds, and then we have the circle in between. Okay. And these are all the notes that are in between Wednesday and today's. And at the end, when I put up the video, I'll put these notes in the folder as well. So aromatic means that the compounds are super stable and they don't undergo reactions that normal double bonds would. We know that if you take a double bond and add bromine to it, you're going to get addition of two bromines. If you use sulfuric acid, which is basically acid and water, you'd get H plus H2O adding. If you use KMNO4, you would at least cleave the bond or add two OHs. If you take bromine or sulfuric acid or KMNO4 and put it in benzene, nothing happens. The benzene does not react. This is why when we looked at saying, okay, if I had this double bond attached to the benzene ring, or actually not the double bond, we had just a single bond, and I said, I want to add bromine and light to this reaction to do a free radical halogenation. I would free radically halogenate at the benzylic position. When I just have a double bond here, I've got to worry about the bromine adding to the double bond. With a benzene ring, bromine will not add to the double bond. So this is perfectly legitimate, and I don't need to use NBS as my reagent. So that's the reason, is because benzene is super stable. Okay. And we could go through the energy diagrams, which we're not going to. And we're not going to talk necessarily about naming except this. When we get to adding groups to the benzene ring, and that's going to be called electrophilic aromatic substitution. When we have a group that's already on the ring, that group is going to be called the director. And it's going to direct the incoming electrophile to go either to the 1,2 position or form a 1,3 disubstituted or a 1,4 disubstituted product. Those have abbreviations, 1,2 being ortho, 1,3 being meta, and 1,4 being para. So we're going to eventually learn those terms of ortho, meta, para for 1,2, 1,3, 1,4. If you're in at least my lab section, we've already said that if you're looking at the aromatic hydrogens in the NMR spectrum around 7, that if you see a pair of doublets in the aromatic region, it always tells you that it's para or 1,4 disubstituted. If it's not, then you don't know whether it's 1,2 or 1,3. But para has a very specific characteristic spectrum. Okay. So that we're going to have to remember, and we'll get to doing those kinds of reactions probably after break. All right. So that's kind of some background on benzene. Let's talk a little bit about what makes a molecule aromatic. And all we can talk about is what rules do you have to follow for the molecule to be aromatic. Okay, and there's no real cause effect here. Well, there kind of is, but we're not going to necessarily get into that. So here are some aromatic compounds that are made up of fused rings. Either the rings are fused or they're just joined together. So this first one is naphthalene. That can be used as mothballs. Sometimes you'll find that. Anthracene has 3 rings fused. If you think of anthracene, if you've ever heard of like anthracene coal, that's where that term comes from. And I'm going to take a little aside here for a moment because these aromatic compounds have a different source and nature than the normal alkanes, alkenes, and alkynes. So if you want, the basic alkenes, alkanes, and alkynes, you get those from crude oil, is where those come from. I'm just talking raw materials. Plants make some aromatic compounds. They make some alkenes and alkenes mostly through Diels-Alder reactions. But for the most part, the mother's milk of alkanes, alkenes, and alkynes is crude oil. Okay. It goes to the refinery. It gets split up. Sometimes long chains get chopped up with catalysts. But that's where alkanes and alkenes and alkynes come from, is crude oil. Where aromatic compounds come from is coal. And so coal-rich countries, like let's say Germany, back in the 1900s, that is where organic chemistry developed. It's not an American science, it's more of a German and probably Russian science, although who knows what was going on in Russia at that time. It was fairly closed society. We just know there's a lot of killing going on sometimes, SARS and things like that. But Germany in particular had all this coal, and so there's a lot of research done by German chemists in order to get raw materials. So if you take coal and you heat coal with no oxygen, because if you heat it with oxygen, you burn it. But if you take oxygen, or if you take the coal and you heat it without oxygen, you basically get volatiles that come out that's called coal tar, because it's tar. And it's made up of a lot of different aromatic compounds. And so that's sort of the beginning of maybe the pharmaceutical industry as well as the petrochemical industry, where people were able to get these raw materials from the coal tar and begin to make different things out of them. One person, William Henry Perkin, who was like some child know-it-all, had a chemistry lab in his basement, which also meant he was well-to-do. He was trying to make quinine to cure malaria. And he started with some coal tar materials and ended up making this purple dye, which didn't cure malaria, but it was the royal purple. So before that, if you wanted to have purple clothing, which symbolized royalty, you had to go to some obscure island in the Mediterranean, dig up these bugs, and then crunch them all up, and that's where the purple dye came from. He was able to make it synthetically, and then that became like a fashion something in Paris. It was the color of the season, I guess. But he showed that you could use these aromatic compounds to make dyes, and then other people used them to make things like aspirin. And if you think about the compounds we used in lab, like aspirin, acetaminophen, even the Aleve, they all have aromatic compounds as their base. So that kind of led people to think about making cures, making medicines from coal tar. So that's why organic chemistry kind of developed the way it did in Germany. So I digress, I'm back. So then you have benzopyrene, and then some of these molecules that have the rings tied together. This is biphenyl. This is polychlorinated biphenyl, which is a PCB. PCBs haven't really been in the environmental news since like 1970s. But these used to be in transformers, electrical transformers that were kind of like on telephone poles. And the old ones were kind of thrown into landfills and stuff. And so there's a place in Buffalo that was the Love Canal back in the 70s, and that's where the PCBs were. And it created a huge environmental issue back in the day. So this is pretty toxic. I think the company that made it, the guy said, "I'll take a bath in it." I don't think he did. It's a pretty toxic compound. And these PAHs, so these are the kinds of compounds you find in cigarette smoke, in sort of overcooked meats. The char has some of these in it. So these kinds of, the PAHs in particular, they're the ones that, besides all the other stuff that goes into your lungs when you smoke, you get these. These are a little bit carcinogenic. And the reason that they're carcinogenic is because they're flat. Because they're aromatic, and they have that characteristic of being flat or planar. So here's your DNA, double-stranded DNA, with your intercalation sites, your grooves. And so flat molecules can just slide right in there and do bad things. So that's why those molecules in particular are carcinogenic, at least from a very, very simple standpoint, without going into all the biochemistry and biology, which I don't know. My one semester of biology senior year, we didn't get into that. I took it at the same time I was taking biochemistry. Didn't go well for the freshmen in the biology class. They had a curve problem. There was none. So it's not a good situation, seniors and freshman classes. Worked out fine for me. So these molecules are flat. And so why are they flat? So here's our two rules for determining whether something is aromatic. And again, what does aromatic mean? It means that it's super stable. And I'm going to say it's super stable relative to some sort of reference molecule. So benzene is super stable compared to alkenes. It won't react with Br2, but Br2 will react with double bonds, conjugated and isolated. So here's our two criteria. Number one, all the atoms in the ring must be sp2 hybridized. If that is the case, the ring will be flat. So the flat ring isn't necessarily the criteria. All the atoms being sp2 makes the ring flat. So this is our first criteria. And then we have to count up the total number of pi electrons, which is called Huckel's rule. Now what Huckel's rule gives us is a list of allowable pi electrons that make a system aromatic. Okay. We could summarize that list. Well, we could explicitly talk about that list in terms of being 2 pi electrons, 6 pi electrons, 10 pi electrons, 14 pi electrons, 18 pi electrons. We could have that whole list of numbers, which can be boiled down to this equation of 4n plus 2, where n is an integer. So when we talk about Huckel's rule, there is a theoretical reason for it, but it's beyond what I want to talk about in this class. What Huckel's rule does is it generates that list of pi electrons that will make a system aromatic. So that's the way I look at it, as opposed to saying, you could just say, if the number of pi electrons, you put it in this equation, n has to be an integer. If you solve for n and it's not an integer, then that number of electrons does not make the system aromatic. Okay, but I like to think of it just as giving a list. So those are the two rules that have to be obeyed in order for a system to be aromatic, for a system to be superstable. That's what we need. Okay. Everybody with me? I guess I should never just ask that question. I should ask it and then demand evidence. So let's play the game aromatic or not. Except we're going to throw in a couple other terms here. So aromatic means that it follows those two rules. Non-aromatic means that one of those two rules is not followed. So the system is not aromatic. And then we can throw in anti-aromatic. So if aromatic is superstable, anti-aromatic is very unstable. So much so that it's almost impossible to make that molecule. Although nothing is ever impossible. Right? Because if people say, oh, well, that compound's aromatic, anti-aromatic, it can't be made, somebody's going to try and make it. And a lot of times they are successful. Nobody's been able to turn a base metal into gold yet. That was the heart of the alchemists, the early chemists who developed a ton of chemistry for all the wrong reasons, because they just wanted to turn stuff into gold, right? They were like the Rumpelstiltskins, turning straw into gold. Except that's where I think that story comes from. Nobody's done that yet. Nobody's been able to make gold out of it. You can make lots of things that look like gold, but it's not gold. So some of these actually that are anti-aromatic have been made for a split second, enough to determine their structures. So in terms of stability, aromatic, super stable, non-aromatic, not as stable, anti-aromatic, very unstable. And I'll give molecules a human characteristic here, that no molecule is going to voluntarily choose to become anti-aromatic. If the molecule has a choice between being non-aromatic and anti-aromatic, it's always going to choose non-aromatic. And you might say, what are the examples of those? We'll get to them. Okay. So let's start looking at these molecules. So we look at this one. Our first rule is going to be, are all of the ring atoms sp2? And in this case, are they? No, because this one is sp3. This one, all ring atoms sp2? Yes. This one, all ring atoms sp2? No, because that's not. This one? No, because that one's not. That one's not. Down here? Yes. And over here? Yes. So always the first criteria, are all the ring atoms sp2 hybridized? Where it's no, we can immediately say those are not aromatic. They are non-aromatic. They just don't have the superstability. Now we look at some of the other, we look at this one and we say, okay, it is. How many pi electrons does it have? Oops. How many pi electrons does that cyclobutadiene have? Each pi bond has how many pi electrons? Give me a number. Correct number. So he said 2. 2 pi electrons per pi bond. So how many does this one have? 4. So that's got 4 pi electrons. Does that fit the 4n plus 2 rule? No. What rule does it fit? The 4 pi electron, or 4n rule. Oh wait, I didn't say the 4n rule. So if you're anti-aromatic, you have 4n numbers of pi electrons. So aromatic is 4n plus 2, anti-aromatic is 4n. So that means that cyclobutadiene is anti-aromatic. It should be super unstable. It is. People were able to make it for a split second, enough to study it. When they studied it, they found out it wasn't square. It was more like 2x4 shaped, because being square is very unstable. But it only existed for a few parts of a second. I don't know if it was milliseconds, femtoseconds. They made it, they studied it, but it didn't last very long. I don't know who they are, so they didn't achieve rich and famous status. And they aren't in a regular organic book, so they didn't receive that. They're not, Markovnikov or Zaitsev or anybody like that. The cyclooctatetraene, the stop sign shaped, how many pi electrons does it have? It's got 8, and so that makes it anti-aromatic. So that's anti-aromatic, and this one is also anti-aromatic. The majority of the ones on this page are not aromatic. And then this one, this was our anthracene from the page before. Just double check, how many pi electrons does it have? 2, 4, 6, 8, 10, 12, 14. It has 14 pi electrons. That is allowed by the 4n plus 2 rule. 4 times 3 plus 2. And so this one is aromatic. And we're going to find out that this cyclobutadiene and the cyclooctatetraene, they don't have a choice. They have to be anti-aromatic. There's nothing they can do to become non-aromatic. I think this one's been made as well, but when it was made, it wasn't flat. So the molecule basically turns itself away from being anti-aromatic by not staying planar. Okay. So those are our 2 rules. That's how we apply it to these kinds of systems. Right. These are relatively straightforward. We can make these things a little bit more complicated by doing either aromatic ions, or what I would like to do is heterocyclics first. So it is possible to make aromatic systems putting nitrogens and oxygens and sulfur in the ring. Let's say that I had this structure. That structure actually will turn out to be aromatic. We'll see in a few minutes or on Monday, depending on how far we progress in this. But does that sort of 5-membered ring or 5-membered, 6-membered ring system with a nitrogen in it, does it remind you of any molecules you might have seen in a biology or genetics class? Or
Looks like the base part of the nucleotide.
so that's ATCG. See, also when I say I don't know that much biology, my fingers are barely apart, I can also be sandbagging you as well. Then I know a little bit more than that. But trust me, not much more than that. So it kind of looks like the base pairs. And if you think about the structure, then those are the ATCGers. Those are what you use to make the DNA, right? Then there's the other ones that you use to make RNA, or the same ones. See, again, now my fingers are getting farther apart. But think about if you were going to design a DNA molecule that you wanted to stay in sort of a double helix. Okay. So if you're kind of sitting from scratch going, I'd like to make that molecule, one of the things you'd like to do is make the molecules that are going to be hydrogen bonded flat so they can kind of fit together really nicely, like they do in a double helix DNA. And then you might want to say, I want to make that core unreactive. So aromatic systems are perfect because they can be flat and they can be unreactive. And so they're going to be your perfect systems to kind of form that double helix. So that's kind of the way I like to illustrate the idea that we do see these aromatic compounds, and they do kind of have a purpose. Whether they were designed that way or not, that's for another part of the university to discuss. Randomness versus some sort of design. We don't get into that, but it's a great idea to have aromatic compounds holding our DNA together. So the question is, how is that molecule aromatic? How is pyridine aromatic? Well, pyridine's aromatic, actually, that's pretty straightforward, but pyrrole or furan or this molecule, once I put a heteroatom in there, the rules can kind of change a little bit. So let's talk about molecules with lone pairs, like this nitrogen. So if I have a nitrogen with an NH group like that, the nitrogen has a choice. It has a choice of hybridization that it can undergo. It could be sp3 hybridized, so that basically we could put that nitrogen in a tetrahedral structure. Could put the lone pair in a tetrahedral structure, and so that nitrogen could be sp3. Now, nitrogen, and if carbon has a lone pair, it also has the ability to put it into an sp2 hybridized state, where now our nitrogen is going to have the three groups surrounding it, but now it's going to put the lone pair into a p orbital and become sp2 hybridized. So any atom with lone pairs, and that includes carbon, and we'll get to carbon probably next week, but any atom that has lone pairs can make the choice to become sp2 hybridized. Now, why would it do that? Here's an example. Pyrrole. Pyrrole has that nitrogen bonded to the hydrogen with the lone pair. If we look at pyrrole and the nitrogen becomes sp3 hybridized, it's not aromatic, because the nitrogen's sp3 hybridized, and so it's not aromatic. You could argue and say, but it's still planar. Well, yeah, because actually in this geometry the nitrogen would have to be in the plane, but that's not the rule. The rule is it's got to be sp2 hybridized. Let's say it chooses to be hybridized. If it chose to be hybridized, then the system would become aromatic. Now, before we take a look at this, and we'll do this next week, let's go back and take a look at benzene. Now, when benzene has the alternating single and double bonds, its characteristic that's shown on one of those slides is that all the p orbitals are parallel to each other. And, you might have the double bond here and here, and the double bond here and here, and the double bond there and there. But then actually, since it's a hybrid, they're all overlapping. So you basically, for benzene, have a system where all the p orbitals are parallel, and there's this continuous circle of electron density and of pi electrons. It's like the benzene has a donut on top and a donut on the bottom, where the donut is the pi electrons. Well, that's what makes benzene aromatic, is that delocalization of all those electrons. So if I take this nitrogen system, this pyrrole, and I leave it as sp3, it can't be aromatic, because in that case, what's going to happen is the nitrogen's going to put the lone pair and the hydrogen into sp hybridized orbitals, and that sp3 orbital, number one, isn't a p orbital, and so it can never become parallel with the rest of them, and now all of a sudden form a continuous chain. But if the nitrogen says, if I just choose to be sp2 and I put my lone pairs into the p orbital, now all of a sudden that p orbital is parallel to the other p orbitals. So now they can all share the electrons. So that's rule number one. Nitrogen is now sp2 hybridized. But how many pi electrons do I have? Well, if I've got a double bond, I've got 2 here, 2 here. And so the nitrogen says, if I become sp2 hybridized, I can now contribute 2 more. That's going to give me 6 pi electrons. And all of a sudden, the molecule is going to become super stable. All I have to do is be sp2 hybridized so that I can contribute my 2 electrons into the pi orbital to now give that overall system 6. And so that's what it does. It chooses to make the system super stable and aromatic. And if you look at this oxygen, this sulfur can also do something like that. That nitrogen already has a pi bond associated with it. So that's where heterocyclic atoms or heterocyclic aromatic compounds kind of differ, is they have that ability to choose. But we'll find out on Monday that the one thing they never do is to choose to put that pair of electrons in the pi system, if that's going to make the pi system 4n. It will never choose to do that because then it's going to become anti-aromatic. Then it's like, no, I think I'll just stay sp3 hybridized because non-aromatic is more stable than anti-aromatic. Okay, so that's what we'll talk about on Monday and kind of finish up this discussion of aromaticity. And I would think that that's probably going to be the end of the material for the exam. There's no homework problems or quiz problems. I'll take your homework so that you've got the weekend if you need to organize for next week. If you have questions, shoot me an email or bring them to class on Monday.